you replace this expression there by a simple mathematical calculation, you can reach a very simplified equation. Forget about this mathematical derivation, because just 10 students, you can just do it one by one, and you can find that the estimated cost, if we reserve the jth smallest element, is like that, a simple equations. Now what we try to increase the reservation little bit. Instead of jth smallest element, let's go to the j plus first smallest element. So we're increasing the reservation. So using the same analysis, find that the cost estimation for reserving j plus first smallest element is like that. So this expression is got similar to that. And we try to find what is the change. If we increase the reservation, does the total cost reduce or it equation? If you subtract these two, and by simple mathematical calculation, you can reach a very simplified form, which is specified as delta E is basically dj plus 1 minus dj. So obviously this will be always greater than, because this is sorted, so this is always greater than 1, multiplied by rk minus tk epsilon k plus j into epsilon k. Rk is the reservation cost per VM, tk is the contract duration, and epsilon k is the discount you get on that. And j is the jth smallest element. We are talking about j and j plus 1. Now this is the main observation found by my students, that how we can use this in our heuristics. So we observed then from that change some good observation we found. What we observed? We observed that this change in the expenditure follow a bitonic rule. What is bitonic rule? We know that the ascending order, descending order, there is a bitonic order. In ascending order, it's gradually increase. In descending order, it gradually decrease. But in bitonic, there is a certain decrease and then it increase. Or there is a certain increase and certainly this decrease. There are two slopes for that. Now, in that case, we observe that if we measure the change between the first and second, the change between the second and third, in that way, if we create an array, we will say initially the change will gradually decrease. And there is a certain point after that it will increase. So obviously that point, this optimal point is the optimal reservation we need to do. And there is a proof. If you are interested, you go to that paper, you can find the proof of that. I'm not going to discuss about the proof here. The second observation that we have performed is that the optimal reservation always a member of the reserved one. It's not like something in between j and j plus 1. So that also we prove that always the reserved one is a part of this demand vector. It cannot be outside of that. No value other than these demands can reduce the cost further. So there is also proof for that. Now from these two observations, we conclude that the optimal reservation is the jth smallest element in the demand vector, where j is the ceiling of tk minus rk by epsilon k. That you can find from here, because all are constant. This d, d, r, they are constants. Only thing variable is j. So initially this is negative. That's why it reduced. Now as you increase the j, after a certain value of j, it becomes 0. And then if you increase j, positive component increase, so obviously the cost will increase. So we can say the optimal value of j is when this is equal to 0. So from there we get j is ceiling of tk minus rk by epsilon k. And the interesting thing that we found from that expression is that it's independent of the values of the demand vector. Give any demand, it's independent, right? So this tk is the 1 year or 3 years, that duration. Rk is the reservation, one-time reservation cost, and this is the discount. That is given by the Amazon AWS service itself. You do not need to get the particular user. So always given the demand vector, find the jth smallest element. And you can find the jth smallest element in linear time, in order of n. You know that about this randomized select algorithm you can use. You do not need to sort the demand vector at all. Without sorting that, we can find the jth smallest element. So we can find the amount to be reserved in order of n. So after that, we basically perform some experiment on that. For this experiment, we use two data sets. One from the San Diego Supercomputer Center Blue Horizon. So actually in the previous class, Professor Nandini Mukherjee showed you the Blue Jeans data centers. So this is also part of that, this Blue Horizon. So from there, we take this. These are the demand for the virtual resources in their lab. And you know the huge amount of supercomputing environment they have. So this data, demand data we take, and also we take another demand data from another data center called the Sandhya National Lab. So these are available in the net. You can also download, or in our repository also, you can get it. What is the reason for this choosing this two? The first one has some uniform distribution. And the second one, you can see the demand has lots of fluctuations. So in non-uniform distributions, we try to observe our performance of our heuristics that we found on both the this uniform and non-uniform environment. And we get a very good results. If you see, the top line is basically no reservation. That means if you satisfy all those demands from the on-demand instance itself, for all that we use the normal virtual machines that I show you in the hands-on sessions. Only launch all the virtual machine and run it. So this is the total cost. So in per 1,000 US dollars, so many, you can see the $1 million you need for running so many, because you are running for 1 month or 3 months. So actually we need to run it for 1 year, but since IPP is NP hard, so we have to reduce it to 1 month and 3 months, because after that this optimal solution cannot be run. But we should, just to show the performance, we use it. Now if you see that our result, this one, this red and dotted black. So dotted black is our multiple contracts, and this one is the highest contract result. You can see it's very close to the optimal one. So most of the time they give the similar result to the optimal found using that NP-hard problem, and what we get from the order of n algorithms. Only for certain cases there is a slight increase, and this increase also very small. However, for non-uniforms, you can see there is a little bit of increase, but still compared to the others, there is a huge saving, and it's very close to the optimal one itself. So this is the first research work that is done by one of my students, Pritam Kumar Shor, and this work we have published in IEEE Transactions on Cloud Computing in 2016. So you can download this paper and go to it if you are interested to find something here. But if you have any questions on this part, I am happy to answer and happy to interact, because interaction makes everything is clear before I go into my second research work. So please, if you have any query on that part, you can ask. Otherwise, everything will be clubbed together. So there is one question from Ajad. Each demand vector previously known. Very good question and been rightly pointed about our future demands. So these demand vectors are known in advance, basically by some statisticians and the domain experts of that knowledge. Because otherwise you don't know what kind of future demands comes, you cannot reserve it. So obviously the future demands are known. These are statistical. So in the result we have shown, we don't consider the prediction errors. So only considering that these are the demands, what is the optimal one. So obviously actual result will be slightly little bit if there is a error in the prediction. But the prediction is a different issue than the reservation part here. Is that clear, Ajad? Hello? Okay. Any more question? In that part of finding that optimal solution, and the second one is how we can consider the spot, and that is just communicated to IEEE Transaction on Cloud